What am I doing? Oh, I'm going to do some electronics this morning. In fact, what I'm going to do is look at the assignments that we've recently done, and I'm going to perform those confabulations. You say, Vishali, I've already done it. That's just fine. While I'm doing that, I'm going to give you some context and understanding of it as we go, and hopefully we'll all strengthen our electronic skills together and do a little bit of imagining of what might happen in the future. I'm going to share for just a moment our canvas where I've already opened up. Which one is this? This is DIG6 servo controller and LED fader. This is a servo motor here that was shown in the picture, and it goes back and forth like this. One of the most common and popular applications of this thing is in a model airplane, where the little ailerons and flaps of the plane have to move this way and that. There are servo motors inside the model plane that have push rods attached. You see this thing here on the end, it has little holes in it. You put a little bent piece of wire in there and let that wire go off, and that push wire, when the thing turns, that wire pushes and pulls on something, and you can control, do model controls with it. I was just musing in my head before class started about how if I had like a little cannon and I wanted to position it, I would put two servos together. I'd have a servo that controlled the vertical and a servo that controlled the horizontal. And at the high school, we have D controllers, exactly the kind of little toggle control, like thumb controller that is on, well, your PlayStation controller or your Xbox controller. And you could design it so that you go like this with the controller, and the servos would turn it this way or that way. Getting it to fire a projectile would be another thing, but absolutely can be done with the electronics that we know. So here I am, I'm going to do the servo controller, and I look down, and all of a sudden, here's this crazy thing. This is what's happening in electronics now. I know enough about electronics, and I can't stress this enough. I know enough about electronics that in my own life, I can go, I want to do that. I want to make that happen. Whether I'm in engineering class or whether I have a project for a different course that I have to do, or it's just in my personal life and I want to do like a fun thing, like maybe I make a holiday decoration where Santa's motorized and you turn around this way and that way. And so I look up on the internet to find the circuitry that does that, because I don't design circuits after taking PW electronics. I'm not a circuit designer, but I understand how circuits work. So I look this thing up on the internet, and there it is, boom, 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 boom. And I say, oh, that'll do what I want it to do. That's a servo controller. Now, how am I going to turn that into a real thing in real life? Kind of like the plasma gun, but actually happening instead of just happening in a fantasy. So what I'm going to need is I'm going to need a 555 controller. I'm going to need a transistor and a variety of resistors, which I've tried to use in the design of this thing, common resistors, a couple of polarized 10 nanofarad capacitors, and 5-volt power supply. So now that I've taken electronics, I know all of these things, I can make it happen. The trouble is, this 5-5 timer that appears in the diagram here does not exist. This is a fake 5-5 timer for circuit design. When my 5-5-5 timer comes in the mail, it's a little microchip that has all the pins, 8 pins around the outside. We know this because we have already designed a 5-5-5 timer in iCircuit with the pins in the right positions. This is designed with the pin out. This is your 5-5-5 timer sub-circuit, which this assignment requires that you build that thing out of this thing. Now, you may have already heard some people say, oh, it gets so complicated and wires going this way and that way. Yeah. So part of being successful at doing electronics is keeping things as organized as possible, making decisions as you go about the best place to put things. One of the things that you always want to bear in mind when you're building electronics is that you want to keep your wire runs as short as possible, because extra wires builds extra resistance into your circuit, and those wires also create magnetic fields that can interfere with circuit performance. So I have not done this before. This is my first attempt at building this circuit this way. And so I'm going to be making the decisions as we go. The first decision I make is that I have a 5-volt rail down the one side and a ground rail down the other side, because that's how my breadboard works. And my breadboard works like that because it's designed to work with integrated circuits like this one. So I plop my integrated circuit down there, and the first thing I do is I go VCC to 5 volts and ground to ground, because of course that's going to happen. I don't even need to look at the circuit diagram to realize that that needs to happen. When I'm using a 555 timer, there are two other things that commonly happen. The not reset is connected to 5 volts. And the reason why is that in order to reset the timer, you pull that pin low. So you actually set that to 0 volts and it resets the timer. I don't want that to ever happen in this circuit. I don't ever want to reset it. So by tying the reset to high, 5 volts, it guarantees me that this thing will not reset in the middle of whatever it is I'm trying to do. So that's a critical thing. This control is used to control the pulse width of the circuit that we're building, and I'm not going to be messing with that. So when you're not messing with it, sometimes you'll see some designs where that pin, the control pin, just floats. It's just left to be whatever it is, which is always kind of a dangerous thing to do in electronics, is to float a pin. And you say, yeah, but Charlie, we've had some designs recently where you left pins floating. Honest to God, the reason why I leave a pin floating is that I don't know where to put it. And then luckily I hit simulate and go, and it actually works. I might run into a problem later on when I actually build the thing and it behaves badly, and I might need to consider that it's because I let a pin float. So this control, because I'm not using it, is connected through a 10 nanofarad, no, 10 nanofarad. I accidentally made it micro. I have to make a correction here. This is a 10 nanofarad capacitor and goes to ground because I'm not using the control pin. That's just the basic setup. Now I have to get into building my circuit. I am not going to switch from one window to the other. So if you want to, you might want to, along with this share, you might want to open the actual assignment to see the circuit that I'm working on. When I'm working on circuits, I often like to work from left to right, but I find that when I'm doing it this way, in a way that's more like prototyping, it's more effective for me to go pin to pin. So on this one, I'm actually going to start with the output pin, and I'm going to connect the output pin to all of the things the output pin is connected to. Well, when I look at the output pin in the circuit, it goes through a 1K resistor into a transistor. So I'm going to drop in a transistor off the pallet, and I'm going to take this output and connect it to that transistor through a 1K resistor. My resistors in iCircuit come off 1K by default, so this is really nice. So I'll take this, that, and connect it there, and I'm going to connect this to the output. You say, Charlie, you went all the way around there. Well, the reason why I went all the way around is because I'm still thinking of this as inputs on the left and outputs on the right. I just can't help thinking about it that way. But now I'm going to look at this transistor. Where does the transistor go? So I came off the output pin. I went through a 1K into this transistor. Well, the one end of the transistor goes to ground. So I'm going to come down like this and shoot all the way over to the ground. And then what is the collector on this thing doing? Well, it goes 4.7K, which is, boy, is a common resistor I have laying around all over the place. 4.7K resistor, 4.7, which is going to my 5-volt rail. And then that connects to the top of to the collector on my transistor. So right here, right now, I have quite a bit going on in this circuit that is associated with my output. First of all, I have a ground wire. See how this wire here is connected to ground? This is one of my signal wires. It's the negative wire on the diagram. Do you see how the negative wire on the diagram is just connected to ground? Well, this is connected to ground. So this is going to be my negative wire. And then coming off the top of the collector, I have my signal wire. There's my signal wire. And then my positive wire going to the servo comes off of 5 volts here. So I'm going to make things look really official and do this like this. Now, I want to point out to you once again, this is the first time I've done this. So this organization that I have here is kind of new. I could put labels on these. I'm not going to bother. I would label this one negative, and I would label this one signal, and I would label this one positive. So by connecting all that to the output, I already have the output stage all created. This is working out great for me so far. I like it, and I can kind of imagine what this would look like if I build it on a prototyping board, because I have kind of a prototyping board philosophy now. The reset and the VCC are already taken care of. Ground is already taken care of. Threshold and trigger. The funny thing about threshold and trigger here is on the 555 default, which you know what, I'm just going to bring it in so I can talk about it, and then I'll delete it. Here's this default 555. Here, threshold and trigger are on the same side. And the reason why is that they're often tied together, one connected to the other. It happens a lot in circuits. Matter of fact, almost all the 555 timer circuits that we presented so far, the trigger and the threshold are connected together. Well, I'm using this thing now, and the trigger and the threshold are on opposite sides of the circuit from each other, which seems inconvenient here. And honestly, from a I'm trying to get things done point of view, that's a little bit ridiculous that I have to go all the way around the chip to connect the threshold to the trigger. And so things are getting complicated. But the threshold and the trigger are connected together, and they're both connected to ground. So I'm going to go right from the trigger here to ground. I'm trying to find a way to make that. Often when you are trying to draw, it makes choices as to what you're trying to select, and it makes me crazy. And I'm going to go like that. That's connected to ground. So I can't help it that wire goes over the top. And this is part of the complication. And I know that for one, Michelle noticed it right away. She's like, Shad, it is getting crazy. Well, some of the other ones are going to be even worse. So the skill that I really have to have, and some of us don't, like some of us are really good at this. There are people who are really good organizers. And there are other people who have difficulty seeing things. I think I'll have an easier time when I do this in Tinkercad and I can color the wires. Coloring the wires will help me keep track of what's input, what's in output, what's going to transistors, what's going this way, that way. So that takes care of trigger and threshold and discharge. Now, all I have to do is take care of discharge. Discharge is the pin on this thing that is actually doing the most. First off, I look at my diagram, and going out of the discharge pin, if you're looking at the diagram in the assignment, which I'm looking at now, but I'm not sharing this diagram, but if you're looking at this diagram, you know what, I'm gonna go ahead and change my share window really quick. I can do it once, it'll be fine. Here I am looking at this diagram. Out of the discharge pin, the discharge pin goes directly to 33K to 5 volts. So when I'm doing a pin, I'm just gonna follow it along the ways that it goes. Over here, it's going to the top of this 10 microfarad capacitor. I haven't even put that in my circuit yet. But just for starters, the discharge goes through a 33K to 5 volts. So coming back to my circuit again, here's my discharge pin. I'm just going to take a resistor, and to keep it out of my way, I'm going to put it way over here. I'm going to take a resistor that's 33. I'm going to take a resistor that is 33K. So let me change it up. 33K. And I'm going to connect it to 5 volts, just like that. And then I'm going to connect that to the discharge. Bang. That's doing that one thing. Now I have other things to do, which includes ramming 2 switches and 2 resistors in here that are coming off the discharge. So from the discharge, I'm going to go through 2 resistors, and I have to do it in a way that's organized. Again, stressing, I haven't done this before. This is my first attempt. So I'm going to put those 2 resistors right here, and one of them is 68K. 68K, that's that one. And the other one is 10K. And there they are. Now they both go to switches. A problem that I know I have in iCircuit is that these damned push button switches, where are they? They go horizontal and you can't rotate them. That's really irritating. I don't like it when it's right up against it like that. Like as an aesthetic thing, that switch is too close for me. So I'm going to take the switch and move it down, which I can't do. How about that? Switch. I'm going to put the switch here so I get a little bit of air between this resistor and the switch. And oh, I was going for push button switches. Darn it. Hang on, wrong switch. I dropped in the wrong switch. Picked the wrong one off the menu.
Does it matter if you change the kind of switches, Charlie?
I'm sorry?
Does it matter if you change the kind of switches?
No, but one of the things when you're working an iCircuit, you want to test a thing. Sometimes you have to do two switches at once, like when you're doing logic circuits. So I use those knife switches so that you can close them and they stay closed. Because if you do a push button, you can't do two push buttons at once. So if I designed a circuit where two switches had to be done, I'm out of luck in iCircuit because I've only got one pointer. That turns out not to be a big thing here because these two push buttons are pushed independently of one another. You're either pushing one or the other, but not both. And actually, because it must be that way, I don't want to push both buttons at the same time in this circuit. Probably best to use the push buttons. If you've done it with knife switches, that's perfectly fine with me. When I come out of these switches, where do I go? Well, let me go back to the circuit again and have a look at it. I come out of these switches, they go together to, you know what? Do you see a mistake that I made? I made a mistake in my circuit design. I made a mistake. Let's have a look at it. I came out of trigger and threshold and I went to ground. That was a mistake. Trigger and threshold don't go to ground. Trigger and threshold, let me switch back. Trigger and threshold go to a place, to the same place as these switches, and all together they go through a 10 microfarad capacitor to ground. So I made a mistake in my design because I was looking at my design thinking of this line as being ground, but it's actually this line down here that's grounded. So I want to be careful about that. I'm gonna bring this switch together with this switch together with trigger and threshold, and that's a bit of a trick on my diagram because I have this switch and this switch that I want to bring together with trigger and threshold. You know what I'm going to take from threshold then? I'm going to go, oh my word, this is going to be something. I'm going to go to here, and I'm going to go to here, and I'm going to go to here. So the two switches are now connected to threshold, which is also connected to trigger. I've got to get from here all the way over to ground. And I'm going to do it like this, and then I'm going to go through a capacitor. That capacitor is spec'd out on my diagram as being a 10 microfarad capacitor. So here it is. Oh, they come as 10 micro by default. So I'm going to take this capacitor and rotate it and drop it in position here, boop, and then connect it. Not connecting things directly together means I can just shift that over and it looks nice. This actually, I'm going to get rid of that because that's not a thing. It looks pretty nice. I can tidy things up a little bit by grabbing this rail and bringing it down here, and I can grab this rail and bring it down here to make my circuit a little bit more compact and pleasing. Honestly, I kind of like it. I could label these edges here. The thing is, does it actually work, or have I miswired it? Well, let's see what it does and see if we can figure it out. Well, first of all, I turn the simulator on and the thing is powered. Off it goes. And I see that there is some current that is running through the circuit. That's okay. When I build these things in real life, I can't see that happening, but I can see it happening in iCircuit. So I'm going to come here to this first button and I'm going to press it and see what happens. Do you see the signal wire, which can't point? The signal wire is this middle one here. When I press this switch, that signal wire starts blinking. Now, to you and I, that doesn't mean anything. But that signal goes into a servo, and the servo has an encoder in it, which watches that. And based on the timing of that signal, the encoder says, oh, you want the servo to point to 0 degrees? And it starts turning the servo to the 0 degree position. And it'll keep going, zzz, and it'll turn the servo until the servo reaches the 0 position, then it'll stop. There are some servos that can go 360 degrees. There are other servos that only go 180 degrees, and the 180-degree servos are actually the more common. So the thing's going to go to 0 degrees and then stop. If I release the button before it gets to 100 or before it gets to 0 degrees, it'll just stop when the signal stops. Notice that the signal takes a bit of time. So there's going to be a lag between when I push the button and when the servo actually responds. That lag might annoy me. If that's the case, then I need some more sophisticated electronics in order to get a faster response. That's part of the evolution of electronics, that people see that they have that issue. Now, the other button, I push it, and look, it gives a higher frequency signal to the signal terminal on the servo. When the servo encoder gets that signal, it says, "Oh, you want 180 degrees? I'll turn 180 degrees," and it'll keep on going until it gets there. If I let off the button, it'll stop. Which means when I push the one button, it's going to turn toward 0 degrees. When I push the other button, it's going to go, and I hit these two buttons, and I can make the servo turn this way, and then this way, and this way, and then this way, and then this way, and then use it to control using just 2 push buttons. That is a 2 push button servo controller. That is electronics on a high level. You say to yourself, Shiley, I never ever possibly could have designed that. Nobody's asking you to. The skill that you're learning in your electronics class is to know what electronics can do, to go looking for it on the internet, find the circuit diagram, be able to interpret the diagram and successfully prototype it. And then that missing skill that we don't necessarily get right now because of the situation that we're in, then you learn how to wire that thing together and debug it and test it, and then it works correctly in real life. Right? Understanding the details of how every little nuanced thing works and why it does what it does, well, that knowledge is very useful to you, because the deeper you understand it, the more creative and effective you can be with the application, and the easier it is for you to find the problems. But the absolute deep electrical engineering level understanding isn't necessary. We just have to learn how to wire things together, and we need to learn the tricks of the trade to make sure that we don't goof it up too badly. I still have a bit of time left, so I'm going to go on to the next circuit on this one, which is a much simpler circuit. Lucky for me, I have saved this thing in its default state, so I can reload this. Uh-oh. I thought I was being clever. Oh, you bugger. Oh, shoot. All right, hang on. New share. I saved the circuit so that I could go back to its default where it was like initially put together. And how do we zoom in? And I thought, well, I'll just bring it back to its default again, and it auto-saved. So I'm gonna go in here and delete the guts of this thing, all of this good stuff that I did, and I'm going to delete all that. I'm going to get rid of this resistor, and I'm going to keep this guy. I'm going to delete that, delete that, delete that, delete that, delete that. I'm going to delete this guy here, and these little bits and pieces, cutting them all off so I can begin building this new circuit, which is an LED dimmer. This one is a little less impressive. I'm trying to, like, in every assignment that I give something that has like a significant appeal. That's I don't want that thing. No. I want my sub-circuit. Try to give something that's like fun to do, and also one that's just practical to do. This is the beginning of holiday lights. It's one thing to turn dimmers on and off. It's another thing to turn LEDs on and off, blinky, blinky, blinky. It's another thing to be able to dim an LED. Believe it or not, there was actually a time not too long ago when LEDs couldn't be dimmed. Dimmable LEDs is a relatively new technology. So this is an LED dimmer, and as such, it's a relatively simple circuit. Notice I've got ground and VCC, so I'm starting my chip in the middle here. I've got my control, which I'm not going to use, so I'm going to hook control through the 10 nanofarad capacitor to ground like that. Also, I don't want this thing to reset while I'm trying to use it. So I'm going to take my reset and connect it to 5 volts. Those are standard things that you say, this is what you do. Notice that this, once again, is a circuit where the trigger is connected to the threshold. So I'm just going to go right around, boom, do that. As I become familiar with using 555 circuits to build stuff, I start to become like, oh, you know how that works. It goes like this. Oh, look, I've got this output here. I'm going to bring it down here into the field where I'm going to be working, because that output's going to go through a resistor into a transistor. Wait a second. Things seem to be getting really, really familiar. Yeah, just need a little bit of practice doing it. And before you know it, you get the hang of it. So my ground is to ground and everything's here. So really, I've got my threshold and my trigger, which are bound together but aren't going where they need to go yet. So I'm going to have to come back and look at that. Notice that I'm leaving the discharge just floating. I left the discharge float, which is generally not a good idea. Maybe we'll try to do something about it. Maybe we'll ground it here, so it's not floating. I don't know. And once I get the circuit working, I'll look at what we can do about it. As I said, the best thing to go about this is pin to pin. So I'm going to start with the output pin, and I look at the output and I see that it goes through a 33K resistor. And that's part of not, knowing how to do circuits, but not knowing everything about the engineering. How do you select that resistor should be 33K? The answer to that is you do a whole bunch of math. And our course, naturally, has avoided all of the very, very complicated math of electronic circuit design. And rightly so. We don't want to do all that math, particularly when the simulator can do the math for us. The collector on this transistor is connected to 5 volts high, and then the collector goes through a 220 ohm resistor, or the emitter, pardon me. The emitter goes through a 220 ohm resistor to ground through the diode. The 220 ohm resistor, that should be familiar to me. That resistor here is a limiting resistor for the sake of the diode. If I connect a diode directly to a 5 volt supply, the diode's going to burn out. So we've become accustomed to seeing resistors in the hundreds of ohms level that are used to bring this voltage to something in the vicinity of 20 milliamps, so that we're not torching this diode. So there the diode goes to ground. And I'm running this thing with the simulator turned on, and I hate that. I find it distracting that the simulator is running while I'm doing a thing. Plus, I like the sort of holiday excitement of turning it on and seeing it work right out of the bag. So my output goes through 33, and the 33K goes into this transistor, which is tied to 5 volts, and the emitter of that goes through a 220 ohm resistor through the LED, pointing the LED in the correct direction and going to ground. I'm a little bit concerned about my ground here. Do you see how the top of the ground? There we go. That's a little bit better. Sometimes when you have wires overlap in I circuit, that's bad news, but I think I recovered and fixed it okay. We'll see if it explodes. Now, I took care of that output. Now, threshold and trigger, they're already connected together, which they should be, but threshold and trigger also connect between the 33K resistor, and I'm going to go back to the assignment again so I can see it. Between the 33K and the transistor, between those two, the threshold and trigger, they come around and they connect right there. So I'm going to take this threshold and trigger from where would be the convenient spot? Here maybe. I'm going to take that and try to connect. Oh, geez. Oh, look what happened. Oh, that happens sometimes in I circuit. It tries to go crazy on you. Let's move this resistor over so I have a spot in between here to get this wire to behave and do its thing. Bang. So now my trigger and threshold come around and they connect to the 33K resistor right between the resistor and the transistor, but that's not the only thing that they do. They also go through a 100 microfarad capacitor to ground. So I'm going to do what I think is the simplest thing here, and I'm going to let that cross over. Notice right here where I just did that, it does not form a dot. A dot means there's a connection. I don't want those wires to be connected there. So I am going to take a capacitor. Notice that these capacitors are polarized, so you want to be careful with the direction that the capacitor points. I'm going to connect that there and connect this over here and make sure that I get the value of that capacitor right. It is supposed to be 100 micro, and it's 10 by default, so 100 micro like that. There's that. I can move it off. Oh, no, I can't. I'm going to leave that just there. Doesn't look very pretty, but that's the way that it goes. So going through that, goes in between, boom, 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 boom. And as I expect, this circuit looks very, very different from the one that I was assigned because I'm using my 555 timer IC instead of the default 555. Let's run it and see what happens. What we're expecting is for our LED to dim and not dim. You know, a thing that I noticed recently is that while these dots that show the direction of the current are really nice sometimes, they're starting to irritate me a little bit. So if I turn those dots off, I find my circuit is maybe a little bit more appealing to look at. And in a future circuit, I've deliberately removed the dots because it's just maddening to look at. And look at that LED. It glows and then it goes off, glows on and glows off, glows on and glows off. When I saw that when I first designed this thing, I looked at it and said, wow, I wish it got a lot brighter. It would be super if that LED got a lot brighter. Well, the brightness of the LED, of course, is related to the amount of current that flows through the LED. So I want to boost the current here. So I thought, well, I know, I'll reduce this resistance. So by reducing the resistance through the LED, I'll increase the current through the LED and it'll get brighter. And look what happens. I broke it. I broke it.
Wait a minute, you're still on the
well, why didn't somebody say so? So the circuit, the LED doesn't get very bright. So I think if I reduce this resistor, I'll increase the current through the LED. And as a result of a higher current, I'll get it brighter. But then I change that resistor and all of a sudden, whammo, it breaks the circuit. And the reason why I'm probably getting into trouble there, it's not simply a matter of changing that 220 ohm resistor, because this current is being supplied by this transistor. So I can only get the current that's going to flow into the collector and out of the emitter. So you see right now, if you look at the current in the collector, it's not getting up to the kind of 20 milliamps that's going to give me a really bright LED. So how can I adjust that? Well, this 33K resistor here is a bit like the tap. So maybe if I change this resistance, I'm going to drop it to 22, just sort of experimentally, to see if I get a brighter glow on my resistor. Well, not really. Let me drop it again. I'm going to drop it to 10K and see what happens. Do you see how dropping this resistor is adjusting the frequency of the thing? So what I need to do if I want one that creates a brighter result at this frequency is I'm going to have to change the voltage at which I run the thing. This is a low voltage dimmer. So if I build a version of it that runs at a higher voltage, then I can source more current from the transistor and potentially light the thing up so that it glows brighter. And so there it is, DIG6, the servo controller and the LED dimmer.